In this video, we're going to take a look at the review for our clock systems quiz. I would like to just point out that you will be responsible from time to time flipping back to this front page, maybe while looking along with the video when you're checking something. While I do have these three charts used for the review on both sides, things like the identities and the inverses are going to be on this side that you might need to reference, and you will hear me mention them throughout the video. So in this problem, for the ampersand, the at, and the percent operations that have been created, I'm asking us to find the identity element for each of these. So if we want to take a look, the ampersand's identity, okay, that ends up being when we would see B, A, R, O, and N repeating both in the rows and columns. We can see that happening in N. So that's the identity for this operation. The at's identity ends up being where we see 9876 repeating, and so 9876 both in the row and the column are happening at the number 7. And for our percent operation, the percent identity is where we will see NOBAR repeating. So NOBAR is repeating in the O row and column, so that will be our answer for this. So remember, if you are asked to defend, show work, or maybe explain your answer in this situation, the identities are what are leaving the elements unchanged when other elements are paired with them. So N paired with a B, an A, an R, an O, or an N, as we see up top, still leaves them B, A, R, O, and N. It leaves them unchanged. All right, it says for each of these, find the inverses. So we'll go ahead and we'll do the ampersand operation first again. So I'll just get ready and set up an answer space for us. So we can go ahead and automatically note that the identity for this one was N, which means it is its own inverse. Now we just need to figure out the other pairs. And so if we look up in the chart, we can see N is formed a whole bunch of times within the chart. Specifically, when O is paired with B, and when A is paired with R. So that means B and O are each other's inverses. A and R are each other's inverses. So there are our answers for that one. At is a little bit of a unique situation. We're going to try to find inverses for 9, 8, 7, and 6. But as I look through this, when 9 is trying to produce 7 as an answer, I can see that 9 with itself seems to do that. And that's it. 8 does not have a 7 in its row or a column. It's a weird situation where 8 does not have an inverse. 7, because it's the identity, is hopefully its own inverse, and that does happen in our chart. But just like what happened with 8, 6 does not have a way to produce 7 as an answer. So 6 also has no inverse. Something to keep in mind for the future, if I'm asking you to solve something that uses the at operation, and I'm trying to find the inverse of 8 and 6, I can't. I might not be able to show work using inverse operations. I might have to rely on simply reading the chart. And then lastly, for our percent operation, I'm going to look at N, O, B, A, and R's inverses. The identity for percent was the O, so I'm looking where O is formed throughout this. And sure enough, O with itself is making O, because the identity is its own inverse. N paired with B, B paired with N, they're making O. So they are each other's inverses, which means A and R both form O. And that ends up making the same pairs of inverses, even though the elements are originally written in the different order as the first one. They happen to coincidentally have the same inverses for a lot of those situations. Not perfectly the same, like O and N are swapped out a little bit there, but for example, A with R, that's still an inverse. So they have some things in common, but they're obviously not the same operations. Okay, it then says, which operations above are commutative and how do you know? And the answer for this one ends up being all of them. All of them end up being commutative because of the symmetry that's there. Okay, they are symmetrical about the operation diagonal. You could say across instead of about if you'd like, if that feels more natural to you. But if we draw in these diagonal lines that emanate from that operation, we have symmetry. Okay, it says prove that at is not associative with an example, also known as a counterexample for this situation. You have heard me say before that there's not one answer for this. There are more than one. I just happen to have one here. I ended up focusing on 6 and 8 since that already seemed to be two situational numbers here that caused weird anomalies going on in the chart. There were no inverses for them. So my counterexample that I just have is that 6 at 8, when you have the parentheses grouped at different locations, does not end up giving us the same answer. So 6 and 8 first grouped together. If I look at the chart, 6 with 8 makes 6. And so then we get another 6 at 8 making 6 again. Whereas 8 at 8 made 9. And then 6 at 9, if I follow 6 with 9, that makes 8. And so these ended up not being equal. All right, this is just about your chart reading skills for these next 6 problems. You just have to make sure you're realizing when it's referencing one operation versus another. So sometimes it's percent, sometimes it's at, sometimes it's a mixture. So the ampersand and the percent operations used the same elements, so we can kind of mix and match them. So please be careful when they're mixed and matched there. I'm just going to go ahead and write down these answers, but you needed to take your own time reading these charts. Please keep in mind we look at the left side of the chart and then we travel along the top for the next element. So here are your answers for these ones. And I will show you inverse operations for some of these other solving for x in the future, but I'll just go ahead for these ones since it does say solve using any method. So you can just go ahead and read the charts yourself that these are the answers. You might have just noticed when I wrote down the answer to question number 7, it actually ends up having more than one answer. And we said that for the at operation, because of the no inverses, some weird stuff was going on there. So that actually does end up showing up here as well. All right, if you need to, pause, check over those answers, but then we're going to be flipping over to the back when you resume. Okay, so we're going to now solve these with inverses. So as I mentioned, you might need to flip to the front page so you can see what the inverses we said are. And so you can double check me and see that I'm telling you the truth here. Okay, now x at 9, well, 9 did have an inverse with the at operation. That inverse ended up being itself. So if I at 9 on the side that is attached to the x, inverses reduce each other out. Whatever I do to one side, I have to do to the other. So the 9 at 9 over there will produce the answer. X is left alone on the other side. And so I end up with x equaling 7. Check out what the inverse was for the ampersand symbol here. You'll notice for the ampersand operation, r's inverse is a. So I'm going to do and a to both sides. The and r and the and a cancel each other out. And on the chart, if I look at what a and a is, it ends up being O. So the answer to that one would be x equals O. And it even works for multi-step problems. So in this problem, I have to get rid of outside of the parentheses first, since that's not involved in the problem at the end when we are trying to evaluate when x is there. So I have to get rid of this percent with the a first. And so if I look at the front on what a's inverse was for the percent operation specifically, a's inverse was r. So I do percent r on both sides. It will cancel on the left. It's not going to be the end, though, because I have that parentheses get brought down. The equal sign gets brought down. And then the answer to n %r gets brought down, which is a. And n's inverse happens to be itself, so I go ahead, cancel it out on the one side, and then a and n ends up being the a. And x equals a is the answer to that one. Please keep in mind, you could check all of these answers by going back to the original problem and seeing, okay, if I put in 7, is 7 at 9 equal to 9? 7 at 9 is equal to 9. There it is. For this one, if I put in O and R, that's A, and I'm getting equals A at the end. So you can check that. All right, our last one here is to create a chart with these following restrictions. So I'm going to go ahead and get my pound, my hashtag, my octothorpe, whatever you want to call this symbol. All those are valid names. I'm going to get that operation in the corner. And then this is supposed to be for 1, 2, 3, 4, 5. So I'll go ahead and I'll make some rows and columns for that. So there's our columns. Here's our rows with 1, 2, 3, 4, and 5 in both of them. So now as I go ahead and I look at this, it says the set is made of those elements. I have that. It is a group. Okay, hopefully you just watched the group activity homework answer key. You'll remember that a group means that it has an identity, which happens to be mentioned right here. It has an inverse for everything, not just the inverse that's mentioned here, but that it's also associative. And we mentioned in that video that associative is cyclical, or it cycles, as the best way to try to get that going in a chart. So I'm going to take advantage of this with a sample answer here. So the identity for this ends up being 1, which means I'm going to copy 1, 2, 3, 4, 5 into 1's row and column. I'm going to make sure that the inverse of 2 is 5. So 2 paired with 5 make 1. That also works the other way. 5 paired with 2 is 1. But because 1 is its own identity, and therefore its own inverse, okay, 2 is 5's identity, that leaves only one pairing left. 3 must be 4's identity, 4 is 3's identity. And so we get those 1s. And what you can notice is 1 must have been pushed back to the end when things then slid forward, and then 1 kept sliding forward again until it would have slid back into its original position on the other side. So we can get that cycling here. So instead of 1, 2, 3, 4, 5, this one it can be 2, 3, 4, 5, 1. And then 3 pushes forward with everything else, and we can have 3, 4, 5, 1, and then the 2 pushes to the back. All of these slide forward, 4, 5, 1, 2, and the 3 cycles to the end. And then 5, 1, 2, 3 is going to be here with the 4 cycling to the end. And so it actually ends up being a way to make sure associative property happens. Even though we can't prove every scenario, that's one that works. At any point you need to, go back and look at any of these examples. But if you also want a little bit more review, you can look back at our old homeworks and notes that we did so far. Thank you.